Digoxin is a cardiac inotropic agent. In this video, we'll study about the molecular mechanism of digoxin as a cardiac inotropic agent. This is a schematic diagram of the cardiac myocyte, and this is the myocytic nucleus. We know about the sodium-potassium ATPase pump. The sodium-potassium ATPase pump is a housekeeping pump. It booms the sodium out of the cell and brings the potassium inside the cell. Let us see a schematic flow diagram of the sodium-potassium ATPase pump. So, the 3 sodium is moving outside the cell and simultaneously the 2 potassium is moving inside the cell. The sodium-potassium ATPase pump is responsible for maintaining the high intracellular concentration of potassium and the high extracellular concentration of sodium. There is another important pump known as the sodium-calcium exchanger. The sodium-calcium exchanger is also a housekeeping pump. It booms the calcium out of the cell in exchange of sodium. So let us see the schematic flow diagram. So sodium is moving inside the cell and simultaneously calcium is moving outside the cell. During the phase 3 of cardiac action potential, when the calcium channels are open, calcium moves inside the cell. The increase in concentration of calcium triggers the release of calcium from the sarcoplasmic reticulum. A manifold increase in concentration of calcium occurs that is responsible for the sarcomeric contraction and the contraction of the cardiac myocyte as a whole. After the cardiac contraction is over, the increased calcium inside the cell is brought to its normal concentration by the sodium-calcium exchanger. The sodium-calcium exchanger, by exchanging the sodium in return of calcium, drives the calcium out of the cell and prepares the cell for the next action potential and the next phase of contraction. So in this way, the housekeeping pump produces an electrochemical gradient that runs the show of the house, and the show of the house is nothing but the cardiac action potential. So the cardiac myocyte, and this is digoxin. Let us recapitulate the flow diagram of the sodium-potassium ATPase pump. So sodium moving outside the cell, potassium moving inside the cell. Let us recapitulate the flow diagram of the sodium-calcium exchanger. Sodium moving inside the cell in exchange of calcium which is moving outside. Digoxin binds with the sodium-potassium ATPase pump on its extracellular surface. When digoxin binds with the sodium-potassium ATPase pump, the pump is inhibited. This causes an increase in concentration of sodium inside the cell. The next action is the increase in concentration of sodium inside the cell retards the functioning of the sodium-calcium exchanger, and the calcium which was extruded out of the cell is not being so because the sodium has increased inside the cell. So the net result is the increase in calcium concentration inside the cell. A small increase in calcium concentration inside the cell is responsible for increase in the cardiac inotropic action, and therefore digoxin acts as a cardiac inotropic agent. So let us summarize at the end. Digoxin binds with sodium-potassium ATPase pump on the cell surface. The sodium-potassium ATPase pump is inhibited. Sodium accumulates intracellularly. This causes a retardation of functioning of the sodium-calcium exchanger. So there is an increase in concentration of calcium inside the cell. This increased calcium inside the cell causes calcium-mediated calcium release during phase 3 of action potential. This causes increased recruitment of sarcomeres during cardiac contraction. And finally, this causes the increased force of cardiac contraction. So in this way, digoxin is responsible for its cardiac inotropic action.